All right, good afternoon, class. This is I believe it's lesson 3. We will be covering section 1.4 in this video. I did want to briefly, however, go over one other topic from 1.3 I forgot to mention. This is including the idea of, in 1.3 we're discussing this idea of linear combinations. However, we can instead look at a set of all possible linear combinations. We're going to have a special name for this kind of set. So we have this definition, and this definition is also going to be relevant in section 1.4. So I want to go ahead and talk about it here before we begin section 1.4. So again, as before, let U1, U2, UP be vectors in some arbitrary space Rm, right? So again, M could be any kind of positive integer. It's referring to the dimension. Are we in R2, R3, R4, so on. This is telling us how many entries are in each vector for U1, U2, so on. We have P vectors in an M-dimensional space. Span of U1 is the set of all possible vectors B, such that B is a linear combination of U1, U2, UP, right? In other words, the span is always an infinite set. We're talking about all possible linear combinations are in this set. So for example, if U1 is 1, 0, and U2 is 0, 1, then the span of U1 and U2 is all of R2. Why is that? Well, remember, as we saw in the lecture for section 1.3, every single vector in R2 is a linear combination of these two vectors. So if I take the span of these two vectors, this is then the set of all possible linear combinations. Because every vector in R2 is a combination of these two vectors, then the span of U1, U2 is actually all of R2, right? So we can use linear combinations to create this special set, which is the set of all possible linear combinations for a given vector. However, depending on what vectors we pick in here, they may or may not be a span for the entire space. For example, I could instead say, well, what is the span of the vector just 1, 0, just U1? I'm not including U2. Well, then this is the set of all possible scalars of right? Because I'm only taking linear combinations of a single vector. And if I'm only I can make it bigger, I can make it smaller, I can flip it in the negative direction, so on and so forth. But this space, the span of 1, 0, is not going to be all of R2. So I'm going to erase this definition up here. Okay. So this is not going to be all of R2. So the span of 0, 1 is going to include the vector 1, 0, but then it's going to include any scalar of 1, 0. I can double it. Maybe it's more in this direction, or I can triple it. Maybe it's even more in that direction. I could shrink it by like 1/2. Well, now it's like 1/2 the size it was. I could flip it in the negative direction. It could go this way, or I can make it go more negative. But the point is, no matter what I multiply this vector by, no matter what linear combination I take of this single vector, I can't go anywhere else besides the x-axis. So the span of this single vector is not going to be all of R2. But if I include U2 with U1, then suddenly that's enough to be able to get every possible combination R2. So this notion of span and when the span of vectors covers an entire space or not is going to be key as we continue in the course. And the punchline is going to be that finding our pivots is going to be the key. R2 is a two-dimensional space. So in order to span all of R2, you're going to need two pivots. Well, lo and behold, if you put U1 and U2 together in a matrix, you end up with two pivots here, just like we would need. But if instead you only have one column, well, that's only one pivot, and one pivot is not enough to span all of R2. The reason for that is that R2 is a two-dimensional space. You can imagine because it is two-dimensional, that means it has two axes you can move in, two directions you can move in. So you need, at most, two vectors to be able to span the space. Now, in fact, when you were first learning in, I don't know, sometime in elementary school, when you were learning how to plot points, you would say, well, how would you plot the point 2, 3? Well, you would say, I'm going to travel 2 steps in the x-axis direction and then go up 3, right? That's how you would plot a point. Well, really, what you were doing was that you were traveling 2 steps in the 1, 0 vector direction, and then you were going 3 steps up in the vertical direction, the 0, 1 direction. Now, these are not the only 2 vectors that span all of R2. In fact, any 2 vectors, as long as you have 2 pivots, is going to be able to span R2. So there's lots of different ways to do this. We're going to talk about this more later in Chapter 1 and Chapter 2, but I wanted to go ahead and introduce this notion as it's going to become more important as we continue. Okay, so this is what span means. Let me now transition to section 1.4. Okay, section 1.4. So we know now how to take linear combinations, right? For some vectors, column vectors, let A1, A2, AN be column vectors in Rm. So again, n and m are different constant integers. I have an n number of vectors, and each vector is in Rm, meaning each vector has m entries if you were to write it as a column vector. Okay. Well, then if I have scalars, let x1, x2, xn be constant scalars. Okay. Then we can take a linear combination of these vectors, as we learned from 1.3, and we can create a brand new vector. Let's call it vector B is our brand new vector. And it is a combination of A1, A2, AN. Okay, so this is a linear combination. Now, linear combinations is how we're going to create equations with matrices. We've already seen from 1.3 that the question of asking is a vector, is some unknown vector B a possible linear combination? We can rewrite it as a matrix problem. So how can we turn this linear combination into a matrix? Well, first, let me introduce our notation here. How are we going to do this? I'm going to let A be a matrix with A1, A2, dot, 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 AN as the columns, right? So there are n columns, and each column has m entries. So A1 has m entries going down, meaning this is a matrix which is an m by n. It has m rows and n columns. Okay. So m then, this is referring to m is the dimension of the column vectors, and n is the number of vectors that we're using in the linear combination. All right, great. So then we can rewrite this as a combination here of the column vectors, but more specifically, I can redefine this matrix equation as the matrix A times X, where X is going to be a new column vector, which is containing all of my scalars, right? So in this fashion, so we've already said we're not going to do vector multiplication, but we can do matrix multiplication. In fact, this is going to be our definition for matrix multiplication. Matrix multiplication is going to be defined by linear combinations. So I'm going to take my matrix A. It has m rows with n columns, and it's being multiplied in this fashion. So we have this formula, AX equals B, and we can rewrite this as a matrix times its vector, or in other words, we're rewriting it as a linear combination where we have x1 times the first column plus x2 times the second column plus x3 times the third column, so on and so forth. This then gives us an alternate way of writing a linear combination, and we can now write all the problems we've discussed so far in a matrix equation format. So let's look at some examples so we can see how we're doing this. All right, so here's our example. As we've discussed in linear algebra, we're in a large sense concerned about different types of systems of linear equations and questions we can ask about systems of linear equations. So here we have another system of linear equations, x1 plus 2x2 minus x3 equals 4 minus 5x2 plus 3x3 equals 1. Now we've already seen from the lesson 1 lecture that we can turn this into an augmented matrix. 1, 2, -1, 4, 0, -5, 3, 1 variables, and the last column matrix. But this question is the same thing as if we rewrite it in our matrix form. If we rewrite this in our matrix form, we're taking a combination of these column vectors. I want to know, how can I add the column vector 1, 0 with the column vector 2, -5, add it with the third column vector, -1, 3, and I want this to result in 4, 1. Well, if I multiply the x1, add these column vectors together, it's going to be the same thing as these equations I have up here, right? But this linear combination is the same thing as matrix multiplication. So I have 1, 0, 2, -5, -1, 3, times the column vector of my x's. In fact, this is going to be our definition for matrix multiplication. Matrix multiplication is a linear combination of the columns, where we're saying how much I am scaling each column by in order to combine them together to result in the b that's on the end. So here's the a, the x, and the b. So when I have x with no subscript, this is referring to its own column vector, which is containing all of the scalars which are being applied to each column. Okay, so we can rewrite them in this form. But now I want to talk about, all right, well, what does this mean to be finding solutions? Or what if I don't know b? What are all the possible b's I can get from some given linear combination, right? What b is going to be able to fit? We've talked about trying to solve for x, but what if instead I'd like to know, well, what b are possible? Maybe I don't care about this b for 1. I'd like to know, is there some other way to combine the columns to get some other vector besides this specific vector? So what vectors are going to be possible outputs from this linear combination? That's what I want to look at next. So let me erase what we have here. Okay. First, before we do another example, let me just also note some other points that we can say, some other facts. So fact 1, ax equals b has a solution if and only if. First, let me clarify, what does this language mean? What does if and only if mean? This is just a term that you're going to see in various theorems or definitions that can appear in different textbooks. The point of an if and only if is to say that the implication of what I'm about to say goes both directions. The fact that ax equals b has a solution, that is going to imply something else happens. But if that something else happens, this if and only if goes both directions. In other words, these two pieces of the statement are equivalent. They imply one another. The fact that ax equals b has a solution implies that b is a linear combination of the columns of A. So we see here as we're adding new vocabulary, we're going to try to start tying all of the vocabulary together. But this goes both directions. If B is a linear combination, that means there is some scalars, x1, x2, x3, so on, that allows me to multiply the columns together so that I get B. Well, matrix multiplication is the same thing as asking, is there a linear combination? These are the same question, just we're writing them out in a different format, which is going to be useful as we continue. Okay, so now let's look at the problem I was just discussing before that fact. Let A be the matrix 2, 3, 4, -1, 5, -3, 6, -2, 8. And let's say x is arbitrary. I have some unknown scalars, x1, x2, and x3. And I just want to know what B are. What B are possible? I would like to know that would be a linear combination. How would I know all the different possible B? Well, to do that, I need to look at, okay, what does it mean to multiply here, right? That means I'm taking A times X. So I have this matrix 2, 1, 6, 3, 4, -3, 8 times x1, x2, x3. This matrix multiplication is the same thing as taking a linear combination. I'm saying I have x1 times the first column plus x2 times the second column. And then I have x3 times the third column, right? But now that I've rewritten it in this linear combination format, I can now apply the scalar, add together. So what do I get? I'm going to have 2x1 plus 3x2 plus 4x3 negative x1 plus 5x2 minus 3x3 6x1 minus 2x2 plus 8x3, right? So while this kind of looks all messy, note this is just a column vector, right? Pick your favorite x1, x2, x3. Doesn't matter. Pick your favorite x1, x2, x3. That is then one possible combination of these columns. Well, whatever x1, x2, x3 you pick, plug them in. This is going to tell you what is that combination. Plug in the x1, x2, x3, you get a new column vector. This is a 3 by 1 column vector. And so matrix multiplication, we can define in this way as a linear combination of the columns. So some key points I want to highlight here. One, notice in order to do this multiplication, I need a scalar for each column, right? If I have 3 columns, I need 3 entries in this vector x. So I want to highlight some of these dimensions because this is a necessary piece in order to do matrix multiplication. For any ax equals b, okay, we've said A is in M by N, right? M is indicating what dimension space are the column vectors of A inside of. N is telling us the number of vectors we're taking in our linear combination. But if I have N column vectors, I have to have a scalar for each column vector, which means X has to be in N by 1. So if matrix multiplication is going to be defined in this way using linear combinations, well, that means whatever this number is and this number is has to match. N equals N. If you have some number of columns, but you don't have enough scalars for each column, you can't take a linear combination, right? Because you have to have a scalar for each column. So A and N, however many columns A has, X has to have that many rows. So in the example we did here, we had a 3 by 3 times a 3 by 1. And what was our resulting vector? Well, the resulting vector, it's a combination of these column vectors, right? I'm adding these column vectors together to get a new column vector in the same space. This B is then also going to be an M by 1 because B is in the same space that the column vectors of A are in, right? If I'm adding the column vectors together and all the column vectors are in R2, well, when you add vectors in R2 together, your output should also be in R2. So this M is going to match this M. So when you do your matrix multiplication, these outside numbers, when you're looking at your dimensions, are going to indicate what your output should be, right? Now, in this case, our B was just another 3 by 1. But if A had been a 2 by 3 instead, then B would be a 2 by 1, right? So B, the dimensions of B, in terms of a vector, do not have to match the dimensions of X, right? X is a vector that's containing the scalar entries. It is not in the same space as the column vectors necessarily. It can be, as in this example, but it doesn't necessarily have to be in the same space. Okay, let me leave that for a moment before we continue. Oh, I see, right. So later in the class, this isn't going to be important yet, but later in the class, we are going to be concerned with, well, it's all fine and good. We can multiply a matrix with a vector right now. But what if I want to multiply a matrix with another entire matrix, right? Not just a column vector, because X is just a column vector. Well, in order to do that, I want to take note of a pattern here, which is going to be super key later in the class. We know we can think of matrix multiplication as a linear combination, but this pattern that is actually happening here is what is called the dot product. Okay, so what is the dot product? The dot product says, and this is a way of determining, how do you multiply two different things together. And it's going to work in this case, but it'll work even if X is not just a vector, if X is a matrix. And we'll see that later in the class. So the dot product says the B sub ij. So I'm using subscripts ij in the subscript of B to indicate which entry of B I'm looking at. So the B sub ij position in B. Now, for our example down here, B, well, it only has one column, right? So the I is referring to what row we're looking at. The J is referring to what column we're looking at. So for this B, since there's only one column, I have B11, B21, and B31, right? But later, if I'm multiplying something instead of just a column vector, if I have a matrix times a matrix, which we'll do later, then B might have more than one column. We're not going to do that yet, but that's coming. That's on the way. So the B sub ij position in B equals row I in A, column J in the X that we're multiplying. All right, well, how does that actually work out? We know A times X is supposed to equal this B, this column vector. So how do we find B11 without having to write out all this giant linear combination we did? Well, B11 equals row 1 in A. Okay, so that's 2, 3, 4 times column J, or sorry, column 1 of X. Well, X only has one column. This is times X1, X2, X3. If X had more than one column, then this piece could change in the dot product. But what have we done here? This is just another way of breaking down what we've already done here. We're saying this result, this first entry of the B column vector should be 2x1 plus 3x2 plus 4x3, which, lo and behold, is exactly what we got down here, right? That's going to fill in the first entry for B. So this dot product is going to be a quick and snappy way of doing matrix multiplication. It might seem a little bit weird and clunky here, but as we continue, we're going to start to do this very quickly, and then you're going to get more used to this dot product idea. So similarly, B21 is going to be row 2 of A, which is -1, 5, -3 times x1, x2, x3. And again, we know this is a linear combination. We get -x1 plus 3, which is what we were supposed to do, having to write out the entire linear combination again. Okay, great. I'm going to leave that for a moment. So there are some other key things here I want to highlight from 1.4. Some special properties with the span. All right. So here we have one of our our first theorems appear. And for theorems, I'm going to abbreviate THM. So let A be an M by N matrix, right? Just like we've been doing. Then the following are equivalent. And this is to say the next few statements that we're going to write down all imply one another. If one of these next statements happen, they all happen. They all are equivalent to each other. They all imply one another. So, 1, for any B in Rm, so note in the back of our mind, we're thinking about this matrix equation, AX equals B. We're thinking, okay, for any B, so we're talking about these are possible outputs. These are possible combinations. So for any B in Rm, the equation AX equals B has a solution. So what is this statement 1 saying? This combination exists. In other words, this is like that special case we were talking about when we had the vector 1, 0, and 0, 1. Remember that u1 and u2? Those two vectors, which when you take the span of them, it was all of R2 because every vector in R2 is a combination of them. Why did that happen? It was because we had enough pivots. In other words, this means we had a pivot in every row. Because in order to span Rm, you must have had m pivots. Well, if you have m pivots, you have a pivot in every row because you can't have more than one pivot in the same row, right? So 2, A has m pivots, a pivot in each row. Now, this does highlight a key point where depending on m and n, the dimensions of your matrix, that might tell you right away whether or not those column vectors span the entire space or not. For example, if A is a 3 by 2 matrix, it only has 2 columns, right? Because it only has 2 columns, that means it only has 2 corresponding column variables, right? There's only 2 column variables. It can only have at most 2 pivots. But if it can only have at most 2 pivots, that means it's impossible to have 3 pivots. So for any matrix where you have more rows than columns, it's impossible to have a solution for every B. So this theorem is going to be super key for some of the problems that you may see in the exercises for this section. Depending on your dimensions of A, that could tell you right away before you do anything else whether or not you could have a solution for every B. Okay? But if you do have a solution for every B, then that means you must have had m pivots, right? You had to have enough pivots to span that space. But this also means, as we've kind of said over and over again, that the columns of A span Rm. Why? Because they have enough pivots, right? For any B in Rm, there's a linear combination. If there's a linear combination, that means it's in this span, right? Because the span is the set of all possible linear combinations. And so that's the last piece here, because remember, matrix equation, with that fact we had earlier, being a solution to a matrix equation, or having a solution to a matrix equation, means you're a linear combination. So this is the same thing as saying for any B in Rm, B is a linear combination of the columns of A. So all 4 of these statements are saying the exact same thing. If one of these things happen, all of them happen. If one of them does not happen, that means all of them do not happen, right? So there's this double implication we can get going here. They're all equivalent things. So if one is true, they're all true. If one of them is false, they're all false. But in particular, if you have an example like this, where you have more rows than columns, then all of these are false. It can't happen because you can't have 3 pivots, right? You can't have enough pivots. And if 2 fails, that means all of them will fail anytime you have a matrix like this. This is a key point I want to highlight here. Okay, good. So some other nice properties we have here with matrix multiplication. So here we have some properties with matrices, just so that we can get used to how this works. So again, if A is an m by n matrix and U and V are column vectors in R n. Now, why do they have to be in Rn? Well, in order to do multiplication with A and U, remember, they would have to have these matching numbers, right? If A has n columns, then any vector I multiply with A has to have that many entries, that many rows. So U and V have to be in Rn in order to do multiplication with A. Now, what I'm getting to is that, well, what if I have A times U plus A times V? Well, just like we have the distributive property with like regular real numbers, we have the distributive property with vectors. So I can factor out this A to the left, and I have A times the vectors U plus V. That's the same thing as taking A times the first vector plus A times the second. You can do it either way, whichever way you prefer. This is equivalent. Now, this also means that if C is a constant scalar, well, again, just like with regular algebra, if you have A times C times a vector, so you have a vector being scaled up, it's okay if you choose to instead multiply the vector by A first and then scale it up. You're going to get the same answer either way. So the order here with the parentheses doesn't matter. We can move things around a little bit. Now, some things we can't do. I can't flip the order of A and U, right? Because remember, U is an n by 1. Well, A is an m by n. Well, if m is not 1, then I can't flip the order. I can't even calculate this. I can't even compute that. If I tried to do that in a calculator, I'd get an error. So you can't flip the order of a matrix and a vector like this. But we do have some leeway with some different things we can flip around as we need to. Okay, good. All right, so next, let's go ahead and take a look at today's participation question. This is participation day 3. Let me make sure it's published. I don't think I've published it yet. Participation day 3. Participation day 3. This is due on July 7th. There's a bug flying around my room. July 7th. Okay, it should now be published. So great. Let's take a look at participation day 3. So here we have a question again, talking about linear combinations, this same idea as matrix multiplication, where it says, given the below vectors, what must H be in order for the vector Y to be a linear combination of V1, V2, and V3? All right, so I'm going to write this on the board for us. All right, so what we're asking is, I've already given you some vectors, V1, V2, V3. I want to know, and Y has something unknown, right? So let me just write what we have on the board. V1 is this column vector, 1, -1, -2. V2 is this column vector, 5, -4, -7. And V3 is this column vector, -3, 1, 0. And then Y is a column -4. We have one piece that is unknown. We want Y to be a linear combination of V1, V2, V3, right? Okay, well, we know it's the same thing as looking at this matrix equation where V1, V2, V3 are columns, right? We want there to be a solution, and we want this to equal -4, 3h, right? We want there to be a solution here. We need to figure out, okay, what h can make this solution occur? So we need to figure out what's going on with this very last entry, right? Well, in order to do that, we know solving this matrix equation is the same thing as looking at the linear combinations, which is the same thing as looking at the augmented matrix. By the end of the class, you're probably going to get tired of augmented matrices because they're pretty much the go-to strategy for all of these problems forever and always. So apologies for that now, but fair warning, you're going to be doing this a lot in this class. All right, here's our augmented matrix. 1, 5, -3, -4, -1, -4, 2, 3. -2, -7, 0, h. Now, what I want is I want a solution to exist, right? So to further clarify what we're trying to do, we want a solution. I don't even care how many solutions there are. I just want a solution to be possible. I just want this y to be a combination. I want to know what h will guarantee y is a combination. Well, in order to have a solution, that means the augmented matrix must be consistent. And this is the key thing. We're pulling back the vocabulary terms we learned in the first lecture. The augmented matrix must be consistent. So how do we know it's consistent? So that means no pivot in the equal column, right? Because if we have a pivot in the equal column, that means we have a row with a bunch of zeros and the leading non-zero entry is in the last column. That means we have a row that says 0 equals something not 0, right? So we have to avoid this scenario. We can't have a pivot in the equals column. All right, we now have the problem set up. We have it written as an augmented matrix. So now, let's see, for the sake of space, I'm going to erase some of this. I'm going to leave up what we want over here. And now we've got to zero in on this augmented matrix. Well, how do we find out if it's consistent or not? We need to row reduce. So row reduction, rewriting it in reduced echelon form. This is the key forever and always in this class. So we need to reduce it. Okay. I'd like to have a pivot in this first position. Great. So I need to get zeros below it. So what am I going to do? I need to modify row 2. So I'm going to take row 2 and I'm going to add row 1 to it. I'm going to take row 3 and I'm going to add 2 times row 1 to it. Right? And again, we can do multiple row operations in the same step. So the first row doesn't change. Now I'm going to have row 1 plus row 2. Well, 1 plus negative 1, 0. 5 minus 4 is 1. Negative 3 plus 2 is negative 1. Negative 4 plus 3 is negative 1. Okay, we got some nice numbers. That's good. And now I'm going to modify row 3. I want row 3 plus 2 times row 1. Okay, 2 times 1 is 2. When I add, we get 0, just like we wanted. 5 times 2 is 10. When we add, we get 3. Negative 3 times 2 is negative 6. So when we add, negative 6. Negative 4 times 2 is negative 8. So when we add, we get h minus 8. Okay, assuming I've done this all correctly. All right, that's all fine and good. We're trying to get it into echelon form because all we're trying to tell is where the pivots are, which means for this problem, we don't have to go through all of the work of getting all the way to reduced echelon form. Echelon form is going to be enough to answer this question because I'm just trying to tell where the pivots are. I'm just trying to tell, do I get a pivot in the equals column or not? So echelon form is going to be enough. So then next, in order to have a pivot in the second column, I need to get rid of this 3. So I'm going to do row 3. I'm going to modify row 3 by subtracting 3 times row 2. So row 1 doesn't change. Row 2 doesn't change. And row 3 is going to become 0. 1 times negative 3 is negative 3. When I add, 0. Negative 1 times negative 3 is a positive 3. So when I add, negative 3. And then when I get negative 1 times a negative 3, that's going to be a positive 3. So when I add, we're going to get h minus 5. All right, let me double check I looked at this correctly. I believe that's correct. Negative 3 times negative 1 is going to be a positive 3. Give us negative 3. Yep. Negative 1 times negative 3 is a positive 3. Negative 8 plus 3, negative 5. Yeah, this looks good. So what have we seen? Well, I have my 3 pivots. So now we got to think back to that theorem we were talking about earlier. My matrix A, which the matrix A is the coefficient matrix, that's excluding the equals column. My original matrix A in the problem we were working with, this was a 3 by 3 matrix, right? I have 3 pivots. Well, then, according to that theorem that we had written, because there are 3 pivots, that means these columns, this column, this column, this column, this column, V1, V2, and V3, because each one has a pivot, this means they actually span all of R3. Well, what does that tell us? That means no matter what H is, I'm never going to have a pivot here because right? So no matter what H is, there's never a pivot in the equals column. So when the question says, what must H be in order for Y to be a combination? It doesn't matter what H is because any H works. So what can H be? H can be any real number. And that is a valid answer for this kind of problem, right? That's going to be our answer for participation day 3. In practice, there are times where maybe you would end up with H minus 5 as the pivot. Well, in order to guarantee this is not a pivot, in order for it to be consistent, you would have to make H 5 in order to make it 0 out. But in this case, because the pivot is not here, we don't care. We don't have to worry about it, right? So H can be any real number, and that is the answer for this problem. Let's see. Let me double check. There was some other questions from some students, and bear with me for one moment. And oh, wait, hold on. Apologies. There's a bug flying up my nose still. Hold on, I'm sorry. There might have been a typo in this problem. Let me make sure I copied this correctly. 1, -1, -2, 5, -4, -7, -3. Gosh darn it. See, and this is the issue with recording videos instead of if I had a live class. Because if I was doing this problem in class with you guys, somebody would have said like, hey, is that supposed to be a 1? And I would turn around and be like, yes, you're right. That is supposed to be a 1. So I apologize. I copied this down incorrectly. If you already typed in h can be any real number, you can go back and resubmit a second time. Apologies for that. Yeah, let me back up because I made a typo here, and that's my fault. V3 is supposed to be -3, 1 here. And that, it's funny, just changing this one number could possibly change the entire problem. All right, let's see what happens. I still need the same row operations. So I guess, firstly, let me just say, what we did here is a possible outcome that you can see with these kind of problems. H being any real number is a possible answer for this kind of question. However, I think we're going to find out something else happens just by changing this one little number here. Excuse me. Right. So row 2, I still want to modify by adding row 1 to it. And row 3, I still want to modify by adding 2 times row 1. But now, when we do this, we're going to get 0, 1, -2, -1. 1 times 2 is 2. 5 times 2 is 10. 2 times, 2 times -3 is -6. And 2 times -4 is -8. Right? But now in this next step, something different happens just because I had this one little typo. In the next step, I still want to get this next pivot. So I'm going to modify row 3. I'm going to take row 3. And I want to subtract 3 times row 1. Well, row 1 doesn't change. Row 2 doesn't change. Row 3, here we go. 1 times -3 is -3. That gives 0. -2 times -3 is a +6. We get 0 here. And then -1 times -3 is a +3. H minus 5. Well, now, lo and behold, what has happened? What is the thing we have to watch out for? There's no pivot in this third column, But depending on what H you pick, you might have a pivot in this last column. So in order for this to be consistent, in order for a solution to exist, I want this final row to not be nonsense, right? In other words, I want no pivot in the equals column. Okay, why is that an issue? Well, if H, for example, were 6, then in this last entry, I would have 6 minus 5, say 0 times x1 plus 0 times x2 plus 0 times x3 equals 1, which is nonsense, right? Which means the only way for this to not be nonsense is that H must equal 5. That was the answer we were supposed to get. I had a hunch something looked wrong, but I didn't notice at first what it was. I had this typo here. Apologies for that. But this is the answer you should type in. So if you already typed in the answer or the past answer that I had written here, that's fine. Go back. You can resubmit your answer a second time and type in the correct answer. Okay, that covers everything for section 1.4. If you have other questions, please, by all means, email me. Let me know. We can talk about it. Otherwise, enjoy the weekend. And I will see you all Monday. Office hours begin Tuesday, and homework 1 is also due Tuesday by midnight. So best of luck. I'll see you next week.